welcome to Zen and the Art of Code Lifecycle Maintenance. In fact, let me advance my slide to my real title slide. I spent quite a bit of time putting this together, so I want to show it. Zen and the Art of Code Lifecycle Maintenance. In fact, I just want to ask, maybe not quite enough to do a poll, so we don't actually have the chat available, do we? I was going to ask how many people actually know the book that this title comes from. So I'm not sure we can actually get that information now, so maybe I shouldn't have asked, but many of you will probably know the book that this comes from. Actually, I see 2 raised hands, so that's a few people at least. But I realise that maybe not everybody knows. We will actually show a bit of the book later. It doesn't matter if you haven't read it, but I will encourage you to do so when we get there. But before we get to that, I just want to talk a little bit about what this talk is about and why I decided to do it in the first place. Now, if you know me and you've seen some of my talks before, you know that I actually do quite a lot of talks at conferences, maybe too many. In fact, I keep track of them on my website, and I was counting them up recently. And it looks like that since 2015, I have, and hopefully you're keeping note of this, I've given 117 talks. That's, since 2015. Now, I don't know why I put this slide in, because now I have to update that number every time I give the talk, but it's not too bad. Why am I telling you about this? Well, as I was going through this, I realised there were actually 4 major themes that I come back to a lot, that most of my talks talk about. Testing, of course. Again, if you know me, you know my association with the Catch2 test framework. Done several talks on functional programming techniques and data structures. Error handling, 2 major talks I've done on that a few times. And if you're in Victor's talk in the same room just before me, he was obviously talking about exceptions. Mine was more of a high level. And simplicity, I've done just 1 talk on that a few times, but it's probably the talk that I've drawn on the most for material for my other talks, and this is going to be no exception, if you pardon the pun. Now, even within those 4 themes, I did find that there was a common thread. And it was only really, when I sat down and thought about it, I thought, yeah, all of these are really in some way just about software quality. That seems to be my sort of driving motivation for most of the things that I talk about. So this talk is taking that step back and saying, let's talk about software quality in general. So I'm going to reference many of my other talks for deeper material and keep this fairly high level. We'll go a little bit deeper in some places. But I think to start with, we probably need to define what we actually mean by software quality. What is it? Because it turns out that that's a bit harder than we might think. To give you an idea, here's a blog post from Derek Jones. He is an author of a book on evidence-based software engineering. So it's a blog that I do like to follow from time to time, The Shape of Code. And in this particular post, it's from earlier this year, back in March, the title is The Aura of Software Quality. So definitely on the right theme. It's quite a longish post, but towards the end, he says that people in industry are very interested in software quality. So far, so good. And sometimes they have the confusing experience of talking to me about it. Interesting turn of phrase. A little bit further down the same paragraph. Software quality is a meaningless marketing term. So that's what Derek thinks. Now, he's not saying that software quality itself is meaningless, just that when people talk about it, what do they really mean? And he makes the point earlier on that actually everyone has their own definition of what software quality means to them. So when you're talking about it, we all have our own different definitions, and therefore we're not really talking about anything. That's the trouble. So we have this cartoon, of course. I'm sure you recognize this. The only valid measure of code quality, WTFs per minute. And the cartoon's funny because we can actually relate to it. There's this idea that software quality might be hard to define, but we know it when we see it. That's the key. And both of those things, the fact that software quality is hard to define, and people have different definitions, and the fact that you know it when you see it, turn out to be the themes of this book. So this is the book the title is based on, Zen and the Art of Motorcycle Maintenance. by Robert Pirsig, an inquiry into values. And rather than software quality, he's talking about quality itself. So it's a book on metaphysics. Quality is the central theme, and he determines that quality is not only hard to define, but it's undefinable. And he goes into quite some depth as to why he thinks that's the case. And this idea that people know it when they see it, so it's this contradiction in a way. But he does try to split quality between what he calls classical quality and romantic quality, where classical quality is that sort of engineering side of how things work, whereas romantic quality is more the design, the how things look or they're used. And throughout the book, you might be mistaken for thinking that he comes down firmly on that classical engineering side of things, particularly the motorcycle maintenance aspect. But actually, by the end, he realizes that you need both. Both of them are essential components to quality overall. Now, this book's quite well known. As I said, it's even though it's quite old now, it's worth a read if you haven't read it before. Slightly less well known is a follow-up book called Lila, where he continues his investigation into quality, and this time he splits it into what he calls static quality and dynamic quality. Now that's interesting because they're terms that we do tend to use a lot in software development for different things, and he uses it differently here. Static quality, or rather dynamic quality, starting with that, is quality sort of in the moment as it happens. You know, when something good happens there and then, that leading edge of reality, he calls it, is dynamic quality. Whereas static quality is, well, once something's there and it's sort of out there, he uses the example of hearing a song for the first time. When the first time you hear it, in that moment, you're experiencing it for the first time, you're appreciating its dynamic quality. A song you've known for years and years, and you appreciate how good it is, but maybe you don't listen to it anymore because it's only got static quality now. And he makes a distinction there. Quite interesting, starting to get a little bit off track. So let's continue, come back to software quality. There is a page on Wikipedia that attempts to define software quality, and there are many quotes on this page from different people that have their own opinions. Many of them are systems theorists. I've put some of the quotes up here on this page. So it's only a selection, so do go and have a look at it yourself. Many of these quotes really relate to what we might call the external qualities of the code. Excuse me just a moment. As in the applicability to a purpose. So if you're working for a company and they ask you to build some software, how applicable is that software to the task that it's intended for? And you can appreciate why this would be seen as the very first aspect of software quality, particularly from people who are systems theorists. I do like Tom DeMarco's quote, down near the bottom here. I think you can see my cursor, third up from the bottom. He's proposed that a product's quality is a function of how much it changes the world for the better. So a nice thought, but maybe a little bit idealistic. So if that's too idealistic for you, Jerry Weinberg's quote, I think, is very pragmatic. Quality is value to some person. I like that. It's suitably vague. Doesn't matter what the value is, doesn't matter who the person is, but if it's offering some value, then it has quality. I remember the subtitle of that book was Inquiry into Values. That's interesting. But nonetheless, it's still a bit of a problem that we all have these different definitions of what software quality is about. And when we're thinking as developers about software quality, when we're thinking about the internal qualities of our code and architecture and design and that sort of thing, it'd be nice if there was some sort of standard that just said, this is what we mean, and we can all agree to it. Well, there is an attempt at a standard. There's the CISQ, that's the Consortium for Information and Software Quality. And similarly to the Zen book, it actually tries to split it into 2 or 3, depending on how you count it, different branches. And the bit that particularly interests us, those internal qualities, it calls structural quality. And it says, structural quality refers to the I don't know why that formatting's gone a bit wrong, refers to the software security, reliability, performance efficiency, and maintainability. So there's a list that we can get our teeth into. Hopefully that'll format better now if I rearrange it like that. And those seem quite reasonable at a glance. Yeah, that they definitely seem like things that are going to contribute to what I think of as quality software. So before I discovered this, I was already putting together this material, and I had my own list. And most of that list consisted of these points: correctness, reliability, performance/efficiency, and malleability/evolvability. And you can see there's actually a fairly close correspondence with most of them. Maybe the most divergent are the security and correctness. There's definitely an overlap, a relationship there, but they are different things. I'm not an expert in software security, so I'm not going to talk too much about that beyond just the correctness aspects. And by correctness, we're mostly talking about being free of bugs, whereas reliability is more about being responsive to different error conditions. So reliability, we both get checked off. Interesting that they have performance efficiency and I have performance/efficiency. In my mind, they're sort of two parts to the same thing rather than a continuum. Maintainability, I put malleability, evolvability, because I'm just a little bit more focused on how you can make things easy to maintain by making them easy to change. So it's just a slightly different focus, but really the same thing. So I was quite pleased that worked out quite like that. But I did add one more to that list that wasn't on there, closely related to the maintainability, but I've put reasonability, how easy it is for your code to be reasoned about, to be able to understand it and hold it in your head. There is this concept of local reasoning that we may touch on a bit later. And actually one more, not on the CI/SQ list because they deal with that on a separate branch, but that's that applicability. The thing that we're talking about on the Wikipedia page, the external quality of your code, how applicable it is to the task at hand. That's obviously important as well, so I'm just going to bring that one back in. So now we have a list of 6 sub-qualities or principles, depending on how you look at it. Now, whenever you have a list of things that you find important, it's always tempting to try and take their initial letters and see if you can make an acronym out of them. And I'm no stranger to that, so I had a go at this. And unfortunately, the best I could come up with here was Mr. Crap, which didn't seem particularly compelling or motivating. So I thought, well, what else can we do? So those two that have the alternates, the malleability, evolvability, or the performance/efficiency, well, we could go with the second word. So let's just collapse those down. And then we've got a different set of letters. And we rearrange those. We can get a slightly better acronym, I think. Career. Now, I'd never really thought of myself as a career programmer, but maybe now's the time to start, because that's what we could think of ourselves if we're trying to embody these qualities. Now, maybe a light-hearted note, but actually putting something together in an acronym can help us to keep focused on it. Just think of something like the solid principles, for example. And in fact, I'm giving a talk at another conference about that later. So, the career qualities then. Let's have a little bit of a look at that. These are all things that we could dig into. We could do whole talks or more on each one of those. In fact, I have done in the past, as we said. So I'm going to leave off digging into them individually for those talks. What I really want, what I'm really interested in here, the thing that sort of struck me over the years as being like the sweet spot of what I'm interested in, is where they cross over, intersect, what the trade-offs are, and where they help each other as well, and what we can do to obviously get more of the latter and less of the former. So this talk is going to be more about the in-between, the interconnections. So we're going to take a few pairings between some of these bubbles and just have a look at those. So to get started, I want to have a look at applicability and correctness. Now we might think of these as doing the right thing and doing the thing right. Both important, we're not disputing that, but maybe one has priority over the other if there's a conflict or a trade-off. And this terminology may be familiar. I chose it deliberately because that we have this maxim that we can trace back to Russell Ackoff, one of those systems theorists that we talked about earlier. He said, it's better to do the right thing wrong than the wrong thing right. You may have heard that phrase or some variation of it. It seems like the right thing, if you pardon the pun. It seems like a sensible phrasing. In fact, the full quote from that paragraph is, the righter we do the wrong thing, the wronger we become. When we make a mistake doing the wrong thing and correct it, we become wronger. But when we make a mistake doing the right thing and correct it, we become righter. Therefore, it's better to do the right thing wrong than the wrong thing right. That makes sense. If you're going down the wrong path, if you go down it more effectively, you'll go further down that path. That's the idea here. Maybe that already raises a little flag for you. Maybe software is not always like that. Let's continue the quote, because this is the bit that most people miss. This provides a context for what he was saying. He said, this is very significant, because almost every problem confronting our society is a result of the fact that our public policymakers are doing the wrong things and are trying to do them righter. That doesn't sound very connected to software at all. As I said, Ackoff was a systems theorist. He wasn't talking specifically about software. Should we think that this actually applies to software as well? Maybe. I'm not saying it doesn't, but there are some different dynamics at play when we do software development because of their ability to change things and how doing the right thing can actually allow us to change things faster. That's a thread I think that's worth pulling at. And I'm not the first person to think of this. In fact, the person that really got me onto this idea was Alan Kelly, someone I know from the Agile community. I went to a talk of his some years ago. Did the title slide from it. He seems to reverse that thinking. Do it right and then do the right thing. By the way, did you notice the animation there? If I go back a slide, look at the bubbles at the top, the blue and the green. Swap over. We're reversing the order here. That's the thing to focus on. So what's he getting at here? Well, there's a few things to unpack here. First, we're not saying deliberately do the wrong thing. That's obviously silly. But Alan's main point is that often, particularly in software, we don't really know what the right thing is until we start doing it, until we start doing something. Then we get some feedback and we can start incrementally working towards what the right thing is. And therefore doing things the right way in a way that allows us to iterate quickly and change direction is going to help us with that. And then he has this slide. So it's still from Alan's talk. By the way, at the end of this talk, I'll give you a link to a page that has all the references for all these other talks on there. So don't feel you need to make notes right now. So he calls this the alignment trap. And it's based on a study that I think there's a reference to on the side of the slide. And based on the data from this study, it's divided up into 4 quadrants, which is really interesting because we usually only tend to think of 2 of these quadrants. So the top right, the yellow quadrant, is where everybody really wants to be. And we're talking about businesses here or companies with an IT component to them. So he says IT-enabled growth. That's where we want to be. Very few companies are in this position. It just says 7% according to this study. Very low spending on IT and pretty good sales growth. So yeah, from a business perspective, that seems to be where we want to be. That makes sense. Most companies, though, are in what he calls the maintenance zone, the bottom left quadrant. 74% of companies on the survey, pretty average IT spending, very low sales. Definitely not where you want to be. Now, that part all makes sense. I don't think anybody would be surprised by that, except maybe how many companies are stuck in that maintenance zone. But what about those other 2 quadrants? This is where the really insightful part is, because the alignment trap quadrant, the top left, fair number of companies are there, but look at this. You've got high IT spending and very low sales. That's almost as bad as the maintenance zone. Compare that to the well-oiled IT, the green quadrant, the bottom right. very low spending, and pretty good sales growth, almost as good as the IT-enabled growth. In fact, lower spending even. So that's already the second best quadrant to be in by quite a long way. And Alan's point about being, agile and easy to change direction means that you can easily get from there up to the yellow quadrant when you're ready to do so. The alignment trap sort of locks you in because you've now made it difficult for yourself to move by not using best practices. So I've laboured this a little bit, even though there's a whole lot of talk on it, because I think it's something that most people are not talking about. It's a really interesting reframing of that old quote. So that was correctness and applicability, just examining a little bit of an intersection there. Let's have a look at another two now. Correctness again, but this time paired with reliability. So correctness here, we're talking more about, say, being bug-free, low defect rates, that sort of thing. And reliability, as we said, it's more about covering all possible scenarios, error paths, unpredictable modes, that sort of thing. So when we're talking about the intersection of this, what are we really talking about? Well, a big part of it actually comes down to code coverage. Because if we measure our correctness using tests, but we don't measure the correctness in all of our code, we are missing paths through our code, and therefore we're going to fail on reliability. So getting code coverage sufficient is a key to maximizing that intersection. Now, coverage comes in a number of different forms. Most code coverage tools you might use, if you've ever used a code coverage tool, will usually work in terms of lines or statements. They're slightly different, but approximately they are the same thing, which makes sense. And it's fairly easy to get metrics from that. And if you're using a practice like TDD, you should end up automatically with 100% code coverage. So that is achievable. Very high code coverage otherwise is achievable if you work at it, which is great. I mean, that's a good place to be, but it can give you a slight false sense of security, because just covering all your lines doesn't mean you've covered all the paths through it, particularly things like exception paths and other forms of error handling. So line and statement coverage alone is not enough, but it can also be misleading. So yeah, as we said, TDD can get us most of the way there. But data coverage or path coverage is, to a first approximation, pretty much impossible to measure through your code. Any non-trivial code, at least, beyond a few stages, it just becomes exponentially difficult. So it's hard to measure, and it's also hard to make sure that you're using techniques that will get you there. What techniques are there to help you in this regard? Coming back to testing, when we talk about testing, we'll often think of unit testing, and we consider the relationship to line-based code coverage there. But there's another type of testing, very closely related, called property-based testing. And if you've been following me, and particularly if you've done my TDD workshop, you'll have heard me talking quite a bit about this. Property-based testing is really about testing the paths that you didn't think of, because it relies on generating random numbers and plugging them into the calls to your code, which means they may not find a problem straight away, but gradually over time it's going to be testing more and more of your domain and may eventually trigger something. And a true property-based testing framework will then try to shrink that to the simplest possible failure case. If you do use Catch 2 for your testing, by the way, it has not full property-based testing support, but generators will actually get you more than halfway there. It doesn't do that shrinking part, unfortunately, but I definitely recommend, if you haven't done so, if you are testing, particularly if you're doing TDD, do look into property-based testing, because it can really help you to find those paths through your code that you hadn't thought of, those boundary conditions you didn't think of, and can increase your reliability as a result. Closely related to that, although I have a little bit less to say about it, is fuzz testing. Similar sort of thing, mostly working with random inputs, but generally at a higher level, often from outside your code, working in, or at least instrumented at a top level, and maybe a little bit more tuned towards finding particular vulnerabilities as well. Look into that if that interests you. And don't forget about manual testing. There's still a place for it. We should automate everything we can, of course. Unit tests, property-based tests, fuzz testing, automate all of that. But you can't beat manual testing for just having a mindset for breaking things. And experienced manual testers are brilliant for that. As software developers, we're usually so focused on building things up and being creative. It just takes a different mindset to actually tear it down. So if you have access to manual testers, really do use them appropriately. Okay, so we talked about coverage. Line and statement coverage. These days, that's easy. The data coverage, property-based testing, fuzz testing, manual testing will definitely help you on that path. But I mentioned error paths, and I think it's worth talking about this more specifically, particularly because they're often hidden, especially if you're using exceptions. It may be very difficult to see in the code directly where the error paths are with exceptions. And it's worth dividing error paths, and apologies for the formatting again, between these two branches, what I call IO errors and disappointments. Sorry, IO errors / disappointments and logic errors or contracts. So let's unpack that. Disappointments are things that you need to be able to handle. You expect them at some point, but you'd rather they didn't. So, is this file there? Yes, it is. I can use it. Otherwise, okay, I'll do something else instead. Does this string contain an integer? Yes, it does. No, I can convert that. Otherwise, I'll do something else instead. So it's a bit disappointing, but you can carry on. Compare that to logic errors. We'll usually call these bugs. Well, this is where, at this point in the code, this should be the state of the world, as I can see it. If it's not, then I don't know how we got here. That doesn't make sense. This is the logic error. And all bets are off at this point. It's undefined behavior. Usually the best thing we can do is to abort the program, ideally with some sort of diagnostic. So this is really the domain of contracts. And I mean that in the more general sense. Don't have contracts in C++ as a language feature yet. Famously, they got pulled out of C++ 20. It looks like they may not even make it into 23, unfortunately, but we will get them at some point. But in the meantime, we still have the assert statement. That can get you a long way there. There are third-party libraries as well. But the concept, if you pardon the pun again, of contracts is the important thing here. We want to deal with that separately to those sort of runtime IO-based errors. So what do I mean by that? Let's drill into it a little bit more. Let's look at an example of a function that tries to convert a string to an integer. We mentioned this just now. So trivial implementation, not the best, but it serves to illustrate the point. Got a string stream we're using internally there. Does the job to an extent. What happens if we call this function with a string that doesn't contain an integer? Well, we should get a 0 out of it. At least my reading of the standard is that should be guaranteed. It does get a little bit tricky to decipher at some point, but it's going to try to work through the strings, starting with a 0 and accumulate numbers as it goes through until it hits the first non-numeric character, which in this case is at the beginning, so 0. It's understandable, but not particularly helpful, because now you can't distinguish that from a string that contains 0. So probably not what you want. Now, that's not what string stream was really designed for. I don't know if we can fault it. Maybe we can. There are ways, of course, to interrogate the string stream to see whether it contained a valid conversion. And if not, we can do something different. So now we can make our string to int function handle that error case. In this case, we're going to throw an exception. That may be a good choice. In my experience, these sort of conversion functions, you'll often want to do a little bit more speculatively. You don't know up front what the string contains. if it contains an integer, I'm going to do this thing with it. Otherwise, take a different course. So maybe using a std optional would be a better choice here. We've had that since C++ 17 now, or longer if you've used first-party libraries. So hopefully we're familiar with it. So now we push this to a more sort of runtime handling, something like this. I'm sure you're familiar with optionals have pointer semantics, so we can test them that way and dereference them to get the value out. Pretty simple, straightforward stuff. No surprises, hopefully. But there is a problem here. A subtle problem, but a problem nonetheless. See, although you can test the optional to see whether it has a value before dereferencing it, there's nothing enforcing you doing that other than convention. If you just dereference a null optional, it's undefined behavior in C++. It may do something you can detect, it may not. That's a bit of a problem being exposed to that. So C++ 23 will give us the magnetic operations, map, bind, and map and then, and or else. Just show you map and or else here, because they correspond to what we just saw. And this allows you to pass lambdas in to these functions. You can see in the map case we get the dereferenced value out. So the lambda that's passed in there always gets the dereferenced value. We never have to dereference it ourselves. So in that sense, it is safer. Of course, you can still do it the old way, but this is just a better way of doing things once you get used to it. That's coming in C++ 23, so that's good. But there are other options here for dealing with disappointments. We mentioned exceptions, an optional, just good old error codes. That they can still be useful. But if you do use them, please use no discard now. Again, because otherwise there's nothing enforcing you actually checking the error code. Even though discard is more of a hint. If you do use error codes, maybe consider std error code as a wrapper for it. It's been in the standard since C++ 11, but still very underused, I think. Maybe boost outcome if you want to go a bit further. Sort of sits somewhere between optional or std expected, we'll mention in a minute, and exceptions. Then look into the future. As well as those magnetic operations on std optional, we've got std expected coming. If you don't know what std expected is, it's very similar to std optional, but in the case where you don't have a value, you have an error type that will tell you why you don't have the value. So you can use it as much more of a replacement for exceptions in that respect. That's also coming in C++ 23. Maybe off further into the future, possibly we'll get so-called static exceptions, a rethinking of exceptions again. See my whole talks on that, but at this point, it's looking perhaps less likely than it was before, but not completely gone away. That's P0709, by the way. And there are other third-party libraries, Boost Leaf, many ways of dealing with errors. It's worth being familiar with them because traditionally we haven't treated these error cases quite as thoroughly as maybe we should if we're looking at reliability. There's one of my talks on it. Okay, so that's I/O errors and disappointments. What about the other side? Logic errors or contracts. Having a look at that. Another example. Another function. This one sort of goes the other way, converting an integer to a string, but this time it's interpreting the month as a month number and will return you a string with the name of the month. Simple stuff. I'm sure you can imagine the implementation. We don't need to go there. But here's the interesting thing. There's an explicit range of the input value, that integer, which is the full range of an integer from -2 billion to +2 billion. Pretty big range, but a very limited domain. That is values for which this function is valid. Only, 1 to 12, presumably. I mean, maybe it's 0 to 11. You're going to have to document that somewhere. Plenty that can go wrong in calling this, but all what we will call the contract of the function. Whenever you have a difference between arguments range and their domain of valid values, you have an implicit contract. There are other forms of contract as well, but very often this is what it comes down to. So how do we deal with that? Well, we could do something like we did before with the disappointments. Do a check and maybe throw an exception, or use one of those other techniques. But in this case, because we're saying this function is only valid for values between 1 and 12, we're not expecting to be called with any other value. So we're doing checking here that is technically redundant, and at worst can actually hide bugs, depending on how you're handling it. So there is a very strong case for saying, no, don't handle this as a runtime IO error. Instead, use something like assert or full-on contracts or whatever the mechanism, but something that's going to say, if you violate this, this is a bug, which may actually be compiled out and not do anything because you're never expecting it to happen. Things like asserts will be in there for debugging during development to help you to get rid of those bugs in the first place. So I'm not really telling you anything new here. Hopefully this isn't surprising, but maybe this isn't that satisfying either, because a lot of people feel uncomfortable about doing this. So let's dig a little bit deeper. First of all, we've got the contract in there that a month must be between 1 and 12, inclusive. And the logic of that is encoded within the implementation of the function. But you as a caller are expected to know it, and there's a very stiff penalty for getting it wrong, which seems a bit unfair, really. So it may be best to factor out that check. For example, an isValidMonth function that we use internally to assert on, and externally we can call that before we call month is string. So if we have an unvalidated integer, and we say, well, I don't know what this is, it might be a month, I can test that before calling month as string. Straightforward, simple enough, but that now looks a bit like that optional problem. We can test it, and we can test it using the same implementation, but we're not required to. It's not enforced by anything. So we can still get this wrong quite easily. So can we do even more? Well, another technique that I've used a lot, and I know some people don't like this idea, so just put that out there. Have a wrapper function that does that check internally. So you could do it this way around, where you say, well, I've got month as string checked. Whatever the suffix is, try to be consistent with it so everybody knows what it means. So in this case, this one will do the checking and then call the underlying function. You might want to do this the other way around. This is actually what I usually do. I'll make the default version, if you like, the one that checks. And that will call on to the one that doesn't check, which has the longer name, and therefore is sort of implicitly not the default version. Baked into the name, this is doing something a little bit dangerous. That's the part that I know some people don't particularly like. There's a bit more we can do, but before we get to that, let's take a little step back. And this is all coming about because of this difference between the argument's range and its domain. It would be nice if we didn't have that problem to begin with. It can rule out a whole class of these sort of problems. For example, in the language Ada, it has bounded integers built in at the language level. So if you look on the Wikipedia page for Ada, it will show you this example, which actually has a date class. You can see there, we've got the month type is in the range of 1 to 12. Exactly what we were just talking about. Baked into the language, enforced at that point. Now, okay, we're not using Ada, we're talking about C++ here. You can do the same sort of thing in C++. There are libraries out there to do bounded integers. I know David Stone had one. Use those if you're working with integers in a certain range quite a lot. That would be good. But sometimes it's actually better to do something even more specific. Now, very simple cut down example here. If you're doing this for real, it might be a bit more sophisticated, but you might want to capture a month in its own class. So it's going to hold that integer internally, but now you've got a place at the constructor to do that checking. So once it's passed the constructor, you know it's always valid. And you can pass it around and know still always a valid month. Now your month of string can take a month type. If you've already got one, you can give it to it. No need to check. But if you don't have one, you construct a month, and at that point of construction, it will, in this case, throw an exception if it's not valid. Okay, but what if you've got an integer that you know is a valid month, but it's not yet in a month type? Still don't want to pay that cost. It's still got that same problem. We just push it back a bit. Well, we can use the same approach. We kind of have a differently named constructor, but we can use a technique like tag types. So just an empty type. Here I'm calling it unchecked tag, whose only purpose is to provide overloads for the constructors. We've seen this technique before, I'm sure. So now we can have the checked and an unchecked constructor. Same thing applies. You could do it either way around. You can have a checked tag and make the unchecked one the default. I think that by the time you've got the this encapsulating type, this correct by construction type for month, you've pushed the point of checking so far back that most of the time when you construct this, it's going to be from unvalidated data. And so you want that default to be the one that checks it. But you've still made it possible to construct it from validated data when you do have that. I think that's the right balance at this point. Maybe you still disagree. Maybe we can have that conversation later. But I'm presenting the techniques, something to think about. Oh, and just for completeness, this is how you might call those constructors. So you can see the unchecked tag there. There's a couple of names here that might be familiar. I mentioned correct by construction to begin with. That month is, once it's constructed, we know it's correct. We can rely on it from there on. Therefore, we get the efficiency of not continually checking. You might have noticed those bubbles at the top. We've now got the efficiency bubble there as well. And the other term that I really like is falling into the pit of success. This is why I like the checked one to be the default, because it's easy to do the right thing unless you really know you need to do something otherwise. So, okay, that was quite a long section. We've still got a few more to get through. They'll mostly be a bit shorter, but let's get moving. Back to our list. I want to pick two more now: reasonability and evolvability. Okay, what are we talking about here? So reasonability. I mentioned local reasoning earlier. We'll dig into that in a second. Is about how easy it is to reason about code, and I find it's usually the domain of simplicity. Generally implies that, and so my talk on simplicity, I talk about local reasoning there quite a bit. But also, I find implies use of functional programming techniques, particularly those correct by construction techniques. We talked about this previously, and also a preference for immutability by default. So not completely banning mutability, that's not practical, but immutability by default and correct by construction, as well as some other techniques, but those seem to be the core ones for aiding reasonability. We'll get on to the evolvability in a moment. One slide that I very often take from my simplicity talk, which I originally took from a talk by Rich Hickey, Simple Made Easy, is this one, where he basically goes back to the original Latin roots for the English words, simple and complex. So a simplex, the Latin word, literally means one fold or braid, whereas a complex means many folds or braids. Simple enough. And these illustrations I actually got from Rich Hickey's talk as well illustrate the point. Notice it's not the number of things, it's the number of crossing over, intersections between things. Now, if you look at the one of the strands on the left, on the simple side, and try to follow it from the bottom to the top, it's trivial. You don't even have to think about it. You know where it ends up. But if you try to do that on the right-hand side with one of the complex strands, even though there's only 4 strands there, you have literally got to follow from the bottom to the top very carefully. That's what complexity does. But by having things crossing over, you lose the ability to just, by looking at it, instantly be able to reason about it. And the more complex it is, the more that happens. And one of the points I make in my simplicity talk is it's only a very small number before that becomes unmanageable. So with that definition of complexity and simplicity in mind, what things in our code make things more complex? Well, here's a list that I put together, partially based on when I do a workshop on TDD. I actually get people to call out suggestions, and I put them up on the whiteboard, and every now and then I update this list. So I've actually got a few more to add now, like templates. But these are some of the big offenders. Won't go through them all one by one, but threading and concurrency may be obvious. Globals and singletons, which are really just globals by another name, basically cause different parts, completely different parts of your code base to have an effective dependency on each other through this shared dependency. So that's an extremely complexifying technique. And that even goes for other sorts of shared state, like shared pointers, even if less so. Mutability is one of the big ones, though, because I think it's very subtle how it causes that complexity. And it really comes down to that local reasoning. Once you have a value for something, if it can change at any point, the only way you can reason about that value is to examine every line of code that it passes through after that point. If it's immutable, or at least const, generally once it's fixed, you know what the value is. You don't have to reason about it changing. So that's the main way that mutability really impacts reasonability and complexity. Leaky abstractions is another one just worth mentioning, because we use abstractions as a way to manage complexity, but because all abstractions are leaky to some extent, we can end up actually having the thing we're abstracting and the thing that we're abstracting it with, and have to work with both of them. And now you've added extra complexity in the attempt to make things simpler, which is a bit of a shame. So we do have to be careful how we use abstractions. I go into that more in my simplicity talk. So lower complexity, or greater simplicity, if you like, means that things are not only easier to reason about, but it turns out they're also easier to test and easier to change. And those three things tend to go hand in hand, because particularly if you're doing TDD, if something is hard to test, it's telling you that this has extra complexity that you should have a look at. And it's going to make things hard to change as well. And again, TDD is all about making things easy to change. So it's showing up a design pressure, a smell, if you like. So there's like a cycle there. Lower complexity makes it easier to test. But if you're testing first, you can get lower complexity. So my magic formula for lower complexity is test-driven development and use of certain functional programming techniques. Hopefully I've sketched in why. See my other talks for more depth. We'll need to get moving to cover the next points. So the next pairing that I want to look at, getting towards the end, is reasonability, again, how you can reason about things, and efficiency, which we said was a standard for performance. So this is often the classic trade-off. You can make things easy to read, or you can make them give them good performance. Does that have to be a trade-off? Why is it a trade-off in the first place? Taking a step back, we have high-level code that's easy to reason about, and we have the low-level machine. And the higher the level of code, generally the further away it is from the language of the machine. So we invented this thing that we put in the middle that we tend to call systems languages. C++ is one of those that tries to bridge that gap, give you some high-level abstractions, but also keep you close to the machine. We say this a lot. The trouble is that machine that we're keeping close to is effectively modeled on the PDP-11. If you've ever seen a PDP-11, they look a bit like this. Tape machines and other modules there. This is an old machine. Things have moved on a lot since the PDP-11 was out. So while Intel processors were sort of inspired by PDP-11 architecture, particularly when it comes to how CPUs optimize your code or your execution of the code, we are so far removed from a PDP-11 view of the world that your attempts to optimize yourself most often will backfire and make things less optimal, unless you really, really know what you're doing. So I'm not saying that that's not possible, but as a rule, we should try to make things easier to reason about, not just for other humans, but for the machine as well. If we can offer guarantees that the compiler can rely on, it can generate code that the CPU can optimize the greatest. So to give you a concrete example, this is an example from my functional C++ talk, where in order to initialize this variable color, we need to call a function and test the result of it. And that means that we've introduced side effects, mutability, and just uninitialized variables. So not a great state of affairs for a few simple lines of code by the looks of it. Now, of course, in C++, we can write that with the ternary operator. Now we've got const. We've got just a simple expression, no side effects, no uninitialized variables, and we get type inference in there as well, which is great. But the ternary operator doesn't scale up, especially to more than 2 branches. So if you have a switch statement like this, then we can't use that in a single expression. But we can sort of fake putting that into an expression by using the technique of immediately invoked Lambda expressions, which I think are well known enough now that I probably don't need to explain it too much, but just in case you've not come across it before, we've also got a Lambda here, and we're immediately invoking it at the end, those parentheses there. So while we do have return statements in here, they're not really visible as part of this. And we end up with the same results. We have const, we have type inference, we have no uninitialized variables. Now, in this case, where it's just an integer or an enum, I would expect, and I have verified this in Compiler Explorer, that it should compile down to essentially the same code. In fact, I think it was identical code as the version with the assignment. But if you have a more expensive type, like something like this that's copying characters into a vector, then I would expect, and I did put this in Compiler Explorer as well, and I was going to show this slide, but there was a problem with it at the end, so I took that one out. But it does generate different code, more optimal code, because it's got less work that it needs to do, because it's got more guarantees based on the fact that you're using direct initialization and an expression with no side effects. So this is an example where using a high level patterns can actually be more optimal. That's obviously not always the case. There's still many cases where optimizing something is going to make something less readable. And for that, there are still other techniques that can help. Thinking particularly about testing, I mentioned earlier property-based testing. Maybe a slight abuse of property-based testing, but this does work. Often, you'll have the case where you have a simple, trivial way to do something that's fairly obviously correct, or at least easy to read, and then a heavily optimized version that is very difficult to follow. Well, you can actually use one to test the other, and a property-based testing framework, or even Catch2, can let you do this. So in Catch2, you have generators. See an example here, we're just generating lots of integers. We can call the first algorithm function and use that to test the output of the second one. Not always quite as easy to do as I've shown here, of course, and sometimes it won't be an exact match. You'll have to build in tolerances and things, but quite often you can use this technique to sort of have your cake and eat it, have the optimized version and the easy to read version, and have one test the other. So it's something to think about. Okay, there's many other intersections we could look at. They're the ones we had time for. So just to summarize, there's actually quite a few that we did get to in the end, including that triple there. In fact, you can see that there are some commonalities there. We've got correctness in there twice. We've got reliability in there twice, and reasonability to evolvability. if we drop that link between reliability and reasonability, we actually get quite a nice little stack there. Not any essential significance to that, but it does make a nice graphic, so nice place to summarize. Because threaded through all of this, while we've been looking at these intersections, there's three things that have come up again and again. We've got use of the type system, testing, particularly TDD, and focusing on error handling. And for me, it's those three things. Those are the things that have come up again and again in my talks that lead to all of these software qualities. There is another thing which will touch all of these except applicability, which I'm not going to talk about in depth now. Maybe I need to do a talk on it in the future. But I think it's worth mentioning because it runs right alongside all of these. And that is the use of static and dynamic analysis tools. Now, I happen to work for SonarSource, who do static analysis tools. In fact, wearing a SonarSource t-shirt here, you can't quite see it. So of course I would say this, but actually the cause and effect is the other way around. I work at SonarSource because I think static analysis is important. So do use the tools that we have to catch the things that we couldn't catch using any of the other techniques we talked about today. I think we just got time for the little coda. So we've sort of finished the meat of the talk now. And just mention this blog post by Michael Feathers. It's quite old now, from 2008. Don't be put off by the title, The Flawed Theory Behind Unit Testing. He's not saying unit testing is flawed. It's actually a really interesting story. You should read it, but I just want to run down to his conclusion at the end, because it, as you'll see, it's quite relevant. In the software industry, we've been chasing quality for years. The interesting thing is, there are a number of things that work. Design by contract works, test-driven development works, so do clean room, code inspections, and the use of high-level languages. So almost everything we talked about today is sort of summarized in that sentence as being part of our pursuit of quality, things that work. All these techniques, he says, have been shown to increase quality. And if we look closely, we can see why. All of them force us to reflect on our code. And in fact, that was his main takeaway here. It wasn't necessarily the techniques themselves that accounted for the quality. It was the reflection on the code that they led to. And he said that's the magic. That's why unit testing works also. When you write unit tests, TDD style, or after your development, you scrutinize, you think, and often you prevent problems without even encountering a test failure. So, looking at the code carefully, according to Michael Feathers, is maybe the single biggest attribute of software quality. So, with that in mind, and thinking about stack of qualities, maybe we can think back to that word Zen. Zen originally meant just meditation. And if we look at the Wikipedia definition, meditation, it says it's about focusing the mind on a particular object, thought, or activity to train attention and awareness and to achieve a mentally clear and stable state. So things like testing, especially TDD, good use of the type system, paying attention to error handling, they all force us to focus the mind on the code and help to train our attention and awareness for those 6 qualities of software design. And that is Zen and the art of code lifecycle maintenance. And there's that link to the page with all the references that I promised. So levelofindirection.com/refs/zen.html. And if you can't remember that, I've got extra levelofindirection.com that, of course, redirects there. But that is the end of my talk. Thank you. And are there any questions? See the Q&A tab. I have a question from Pavel about property-based testing. Does property-based testing mean that when you change the implementation as opposed to the interface, you necessarily have to change ranges in tests? I think there's a simple answer to that. Whenever you change an implementation, if you're testing the wrong thing at the wrong level, probing the wrong thing, there's always the danger that you have to change the tests. But if you're testing against an interface and that interface is very clear on what its contract is, and those things haven't changed, then whether you're doing property-based testing or example-based testing, you shouldn't need to change that. But if you do change the contract, then that may be the case. I think it's more of a contract thing than a property-based testing thing, if I understood your question correctly. Feel free to ask it again if I didn't quite get there. Or if anyone else has any other questions. I think we're at time, but we could probably squeeze one in. Yep, Pavel says I got it, and I see the question from Alan Lee. I think I missed what the unchecked tag in the month constructor was. Could you explain that one more time? Yeah, so because constructors you can't you can't have different names for, we can choose a constructor through overloading. So by having an empty type, doesn't have anything in it, just a completely empty struct, we can pass a default constructed version of that struct as an argument, just so that you can select the right constructor through overloading. And the compiler should optimize it out so it doesn't actually add any overhead. Very similar to having labels in some languages in a way, but we're just abusing the language as usual. Hopefully that explains it for you.